Welcome to the dreaming brain, where time slows and darkness gently wraps around the mind. Tonight, we travel into a hidden corner of the universe, a realm where matter is crushed into unimaginable forms, where silent strength bends the very fabric of space. These are the remnants of brilliance long extinguished, waiting in stillness for us to lean closer and listen. A room at dusk holds a silence that is deeper than any book can record. On the wall hangs a clock, its glass cracked, its mechanism long damaged. Yet if one looks at any ordinary clock that still functions, one fact remains. Its hand turns only forward. Even when a clock is broken, our memory of it insists that it once moved with that inevitable rhythm. Time, in the most mundane gesture, reveals itself as a one-way street. Milk spills onto the floor and never leaps back into the bottle. A shattered plate does not reassemble itself in reverse choreography. We age day by day, never becoming younger. The fact is so common that it rarely provokes astonishment. Yet once the mind lingers on it, it becomes one of the deepest riddles of science and philosophy. Why does time age? The question seems deceptively simple. After all, when we step into the flow of a river, we are carried downstream, not upstream. We equate this to time. We are carried from past to future, unable to reverse the stream. But rivers are shaped by gravity and terrain. If one could shift the landscape, the river might change course. Time, on the other hand, has never been witnessed to flow the other way. It seems less like a river and more like an arrow fired once, never to be recalled. The term arrow of time emerged in the 20th century, given voice by Arthur Eddington. It captures the intuition that time is not just a dimension, like length or height, but a dimension with a privileged orientation. The arrow pierces the present and leaves us behind in the wake of the past. Yet here lies the paradox. Most of the physical laws that govern our universe appear to have no interest in such an arrow. Newton's equations work equally well, whether we imagine the film of events playing forward or in perfect reverse. The same is true for Maxwell's equations of electromagnetism, and even the Schrödinger equation of quantum mechanics. The microscopic rules are indifferent to direction. Reverse the velocities of every atom in a box, and the equations predict that the atoms would precisely retrace their paths. In that mirror universe, shattered plates could reassemble, spilled milk could climb back into the glass, and the old might grow younger. Nothing in the mathematics forbids it, but in the world we live in, such things never happen. The asymmetry we experience, the stubborn refusal of events to rewind, cries out for explanation. We usually lean on intuition, saying that the arrow exists because of disorder. We know it by another name, entropy. The second law of thermodynamics tells us that in an isolated system, entropy tends to increase. That is why hot tea cools to room temperature, but never spontaneously becomes hotter. It is why perfume disperses through a room, but never recollects into its bottle. Increases in entropy give us the sense that time has direction, that events unfold irreversibly. The past, then, is the region of lower entropy. The future is the region of higher entropy. But if that is true, it raises another riddle. Why was the universe ever in a state of low entropy to begin with? If disorder is so natural, why did the cosmos not begin already at maximum disorder? To start low and climb high implies an arrow written into the very birth of everything. Even before we confront such mysteries, there is the intimate evidence of our own minds. You and I remember the past, but never the future. The sequence of our memories is aligned with the increase of entropy. It is as if the brain itself is a small entropy machine, fixing one-way traces of experience while discarding the alternative. Our sense of causality grows from this. The cause comes before the effect, never after. Yet, if one returns to the equations, causality is nowhere explicitly written. The electron does not know which moment is future. The planet in orbit does not recognize past from present. Still, our lived experience insists on an asymmetry so fundamental that to imagine its absence is almost impossible. Children sometimes play with the rewind button on old tape recorders or digital players, laughing as voices tumble backward into strange syllables. For a moment, we glimpse how alien the world would seem if everything truly reversed. Imagine waking to find the sun sliding down into the horizon in the morning, the coffee leaping back into its pot, words flying back into mouths before thoughts have been spoken. The very notion is comic, absurd, almost frightening. It reveals how deeply woven the arrow is into every detail of perception. And yet, on paper, the universe would allow such a possibility, if only the initial conditions were set just right. The difficulty is not that reversal is impossible in principle, but that it is unimaginably improbable. To see the film run backward requires aligning every particle into a conspiracy against entropy. The odds are so low that they approach zero in any practical sense. The paradox has haunted science since the 19th century. Ludwig Boltzmann, pioneer of statistical mechanics, offered the bold view that entropy is about probability. Systems evolve from less probable states to more probable ones. A tidy room is only one configuration among countless messy ones. Thus, time's arrow is the tendency of systems to wander into the vast spaces of disorder. But this explanation left behind what is sometimes called the past hypothesis. It simply assumes that the universe began in a highly ordered state. Without that assumption, the reasoning collapses. To many philosophers and physicists, this is unsatisfying. They want to know not just that the arrow exists, but why the bow was strung that way in the first place. As the light in the room fades, the broken clock remains a quiet witness. Its frozen hands remind us of the fragility of our instruments, but also of the certainty that time never rewinds. The clock will not heal itself. It will only gather dust, further disordering with each passing day. Even in its stillness, the arrow is present, for while the hands no longer move, the wood warps, the gears corrode, the air molecules bounce ever more chaotically. Entropy continues its quiet march. The silence is not timeless. It is the soundless unfolding of one-way change. And when we step out of the room, carrying the memory of it, we confirm once more that we walk forward, not backward. Thus begins the story of the arrow of time, a mystery that hides inside every mundane experience, yet challenges the deepest theories of physics. It is a puzzle where everyday intuition meets the indifference of equations, and where the familiar certainty of forward motion meets the haunting question: why only forward? In the chapters to come, we will trace this arrow across physics, cosmology, biology, and even the fragile landscapes of dreams. For now, let the broken clock stand as a symbol: cracked glass, silent gears, but still embedded in a universe where time points in only one direction. Step into the kitchen and watch a kettle sing. Steam rises and swirls, vanishing into the air. Nobody waits for the vapor to condense back into liquid droplets and crawl obediently into the kettle's spout. A puddle forms on the floor when a glass tumbles and shatters, but no one lingers in hope that the shards will leap together, glass reforming, water gathering in perfect defiance of probability. The one-way quality is so banal, so taken for granted, that we almost never question it. Yet each of these everyday spectacles is an emblem of the arrow of time. They whisper the same message. Processes unfold toward disorder, not away from it. Tea cools, bread grows stale, ink disperses in water, and our own bodies betray the passing years. The ordinary is where the deepest asymmetry of nature reveals itself most starkly. Consider the stirring of milk into coffee. The moment the swirl begins, patterns appear, eddies curl, cream snakes into black liquid. For an instant, order is visible in filaments of white and brown, but almost immediately those delicate structures dissolve into uniformity. The final state is dull, featureless, irreversible. There is no law of physics that says the patterns could not re-emerge if every molecule coordinated in the perfect rehearsal. But in practice, the molecules obey the overwhelming arithmetic of probability. There are vastly more ways for the milk and coffee to be mixed than to remain separate. The universe seems to have chosen the path that leads from the improbable to the probable, from structured rarity to featureless abundance. And in this choice, we recognize time's invisible direction. Think of footprints left in sand. The wave comes in, wipes them away, erases the sequence of steps as if no one had walked there at all. We never watch waves assemble footprints, sculpting the precise pattern of toes and heels in reverse. Instead, the past is where footprints exist. The future is where they fade. The ocean participates in time's asymmetry as much as the ticking of a second hand. This is why memory, too, feels aligned with entropy. We recall the path behind us because it left impressions. But the sea of the future has not yet swept forward. No impression is there to be remembered. Oh, children instinctively sense this when they play with building blocks. A tower requires careful arrangement, block upon block, balance, and precision. Toppling, by contrast, requires nothing but a nudge. The collapse happens faster, easier, and more reliably than the construction. The difference is not in the raw mechanics, gravity acts the same, but in the number of possible states. There are many more ways for the tower to be broken than to be intact. Entropy rules in the playground as surely as in the laboratory, and children laugh at the inevitability of falling blocks, not realizing they are rehearsing one of the deepest truths about the universe. We could imagine watching a film reel in reverse. Ashes gather into wood, a candle grows taller as wax streams upward, raindrops rise to form clouds. The image provokes unease because it conflicts with every intuition we have gathered from living. Reversal is foreign, even though physics on paper might permit it. The unease tells us that the arrow is not merely intellectual, it is experiential, embodied. Every gesture, every breath, is saturated with its direction. Inhale, exhale, and the air will not return to the lungs spontaneously. A heartbeat surges, and we know instinctively that it will not beat backward. To live is to be carried along a tide that flows only toward tomorrow. Even the simplest acts of cleaning or organizing reveal the hidden labor of fighting against the arrow. Dust accumulates, papers scatter, order dissolves unless maintained by constant effort. To impose order is to push against the current. It is never permanent, always temporary, like stacking stones against a rising tide. The house tidied in the morning bears evidence of entropy's victory by nightfall. Crumbs reappear, dishes pile, air grows stale. The arrow is relentless in the background. Entropy is patient, and patience guarantees victory. Yet this everyday inevitability masks a puzzle. If the microscopic rules are reversible, then why should macroscopic processes be so one-sided? Why can't the molecules of steam reassemble into water in the kettle? The answer offered by statistical mechanics is that such reversals are possible in principle, but so fantastically improbable that the universe effectively never permits them. To see steam condense itself perfectly back into liquid without external intervention would require a conspiracy of molecules so unlikely that the lifetime of the universe could pass without a single instance. Entropy is not about impossibility, it is about overwhelming likelihood. The arrow is probability made manifest. We sometimes marvel at rare counterexamples. A messy room can be tidied, a chaotic garden pruned, a broken bone healed. But notice, in each case, order is restored only because energy is expended, because work is done. We pay for temporary islands of order with the production of disorder elsewhere. The vacuum cleaner disperses heat, the gardener sweats, the body consumes calories. Entropy in the larger system always increases, even when we create local reversals. This is why life itself, intricate and ordered, does not violate the second law. Living beings maintain their fragile order by exporting disorder into their environment. The arrow still holds, even as we carve brief sanctuaries within it. The arrow of time therefore saturates the ordinary. It is not only in the stars or the collapse of galaxies, not only in the birth of universes or the fate of black holes. It is in tea and milk, towers and tides, dust and dishes, footsteps and fading memories. The fabric of everyday life is woven from irreversible threads. Each act confirms the asymmetry. The beauty of it is that we do not need a telescope to see the universe's law. We need only look at a cooling cup of coffee, a melting ice cube, or the quiet pile of laundry that gathers in the corner of the room. The paradox grows sharper as we gather these images. If physics at its root is reversible, and yet everything we witness is not, then something profound is hiding in plain sight. The everyday is not trivial. It is the evidence, the clue, the stage where the arrow of time is most vividly displayed. The laws may speak indifference, but the world insists on direction. And so, we begin to suspect that the arrow is not an illusion, but a fundamental property that requires explanation. It is carved into our tea, our towers, our sand, our breath. To ignore it would be to ignore the testimony of the ordinary itself. Open a deck of cards, freshly arranged from ace to king, each suit in perfect order. With one shuffle, the pattern is broken. With 10 shuffles, the structure is gone. What was once improbable, a perfectly neat sequence, is destroyed in an instant, replaced by the chaos of random arrangements. The cards are still bound by the same laws of motion. Nothing mysterious guides them, yet we instinctively know. Order vanishes, disorder prevails. Entropy is the name we give to this transformation, and it lies at the heart of the arrow of time. Entropy is often defined as disorder, but this word is only a metaphor, an attempt to capture a subtler statistical truth. In the 19th century, Ludwig Boltzmann imagined gas molecules bouncing in a box. Each particle could be anywhere, moving in any direction, carrying any energy within the laws of conservation. There are countless microscopic possibilities, but when we step back, we describe the box in broad strokes: pressure, temperature, density. A low entropy state is one where the molecules are arranged in a very special way, such as all of them crowding in one corner. A high entropy state is one where they are scattered uniformly. The mathematics tells us there are astronomically more ways to be scattered than to be clustered. Entropy is the measure of that imbalance, the logarithm of the number of possible configurations. And the second law of thermodynamics is its verdict. In any isolated system, entropy almost always increases. This law is not optional. It is as fundamental as gravity, as relentless as the speed of light. But it differs in character. Gravity pulls, electromagnetism attracts and repels. Quantum laws vibrate with uncertainty. The second law does not force systems forward. It simply declares that the overwhelmingly likely direction is toward higher entropy. It is probability elevated into destiny. When a hot object cools, when smoke disperses, when a memory fades, entropy's arithmetic writes the script. The molecules could in principle conspire to move the other way, but the chance is so small that the universe might end 1 trillion times over without such a miracle occurring. In practice, irreversibility is absolute. To glimpse this, think again of shuffling cards. The neat ordered deck is one state among 52 factorial possible permutations, an inconceivable number so large that if every person on Earth shuffled one deck per second for the age of the universe, the chance of finding the deck back in perfect order even once would still be virtually zero. Entropy's arrow is not about impossibility. It is about the tyranny of numbers. We inhabit a universe that bows to those numbers at every turn. The elegance of the second law is that it unites the trivial and the cosmic, the cooling of tea, the rusting of iron, the decay of a star. They are all the same story told in different accents. Entropy governs the fate of galaxies as surely as it governs the melting of ice. Our perception of time's flow, the sense that moments slip away irretrievably, is tied to entropy's march. The past is where entropy was lower. The future is where entropy will be higher. In this framing, time itself might be nothing more than the bookkeeping of entropy. But such neatness raises discomfort. If the second law is statistical, then why is the arrow so absolute? Why do we never, even once, glimpse a local reversal? Smoke undispersing, heat flowing cold to hot, cards jumping into ordered sequence. The answer, again, is probability. Systems contain such a vast number of particles that the odds of reversal are beyond astronomical. For a box of air, the chance that all molecules gather in one corner is so vanishingly small that it might never occur across the entire lifespan of the cosmos. The arrow feels absolute because it is supported by the sheer weight of improbability. Yet, Boltzmann's picture carried a haunting implication. If entropy always increases, then why was the entropy of the early universe so low? A shuffled deck tends to remain shuffled. A messy room tends to stay messy. For entropy to rise, it must have once been lower. The cosmos began in an improbably ordered state. This past hypothesis is one of the great unsolved puzzles of physics. Why did the Big Bang not emerge already in maximum disorder? Why was there a path for entropy to climb at all? The arrow of time is etched not only into today's tea and tomorrow's ashes, but also into the very beginning of existence. The second law works because the first page of the cosmic story was strangely neat, astonishingly special. To make sense of this, physicists have crafted analogies. Imagine rolling dice billions of times. Once in a while, by sheer chance, the dice will all land on 6. That rare outcome is like a low entropy state. But in practice, dice scatter across faces, producing ordinary sums. The Big Bang, however, seems to have rolled an almost impossibly unlikely hand, setting the universe at the start with extraordinary order. Since then, entropy has cascaded upward, writing the story of stars, planets, and life. But the riddle remains: who or what loaded the dice? Or is our perception of low entropy itself misleading, an artifact of how we measure the cosmos? Entropy also provides a haunting glimpse of the universe's future. If it always increases, then the endgame is bleak, heat death, a cosmos in which energy is spread so uniformly that no work can be done, no stars shine, no structures form. It would be a night without dawn, a silence without echo. The arrow that began in the low-entropy dawn of the Big Bang ends in the high-entropy dusk of eternal stasis. Between those two extremes lies everything we call history. In that vision, the arrow of time is not just about teacups and shuffles. It is about the ultimate fate of everything. And yet, we persist in small rebellions. Life itself creates local order, defying the trend with gardens of complexity, brains that weave memory, cultures that carve meaning. But even these defiants are temporary. The cost is entropy exported outward. We keep our bodies alive by consuming food, releasing heat, and scattering waste. Civilization keeps its cities alive by burning fuel, releasing carbon, dispersing energy. Every triumph of order comes with a greater tide of disorder. The arrow holds, even as we carve shapes against it. Entropy is not our enemy. It is the background score to which all existence dances. The second law, then, is not only a law of physics, it is a law of experience. It is the reason we grow old, the reason we remember, the reason we fear the irreversible. When we say time flows, what we mean is that entropy grows. The clock ticks, but its tick is only a translation of entropy's arithmetic into sound. The candle burns, but its flame is only entropy climbing upward. Even our thoughts, these very words, are patterns etched in neurons, consuming energy, scattering heat, raising entropy. We live within the second law, each moment a step along its path. Thus, entropy is more than a statistic. It is the storyteller of reality. Its law is the pen that writes every chapter, from the fusion in stars to the cooling of tea. It is impartial, patient, inevitable. And in its march, we find the origin of the arrow of time. The arrow does not come from the equations of motion. It does not come from the structure of space or the rules of electromagnetism. It comes from entropy, from the asymmetry between the improbable and the probable. That is why the shattering of glass feels natural, and its reversal feels absurd. That is why we move forward, not backward. That is why the broken clock on the wall is never repaired by silence alone. Imagine a theater where the film reel can be played either forward or backward. On the screen, a man drops a ball. It falls and bounces. Reverse the reel, and the ball leaps up into his hand with the same elegance. In the mechanics of Newton, in the symmetry of Maxwell, in the equations of Schrödinger, both films are equally valid. Nature, written on the chalkboard of mathematics, is indifferent to which way the reel turns. But when we leave the chalkboard and walk into the world, only one reel ever plays. The ball drops, the glass shatters, the coffee cools. We never see the reverse. And so, the puzzle emerges like a thorn. Why do the laws of physics admit both directions, while reality insists on only one? This is the essence of Loschmidt's paradox. Johann Loschmidt, a contemporary of Boltzmann, raised the objection with disarming clarity. If entropy increases because systems evolve into more probable states, then what prevents entropy from decreasing when we simply reverse every motion? If one could take the positions and velocities of every atom at a given moment and flip their directions, the equations would predict a precise rewind. Ashes would gather into paper, paper would unburn into tree, tree would stand again in the forest. The equations would not flinch. But in life, such rewinds are absent. Loschmidt asked the question that still haunts us. Why does entropy always move upward when the laws permit it to move either way? Boltzmann's statistical vision was brilliant, but Loschmidt exposed its vulnerable seam. Boltzmann had argued that entropy rises because there are more disordered states than ordered ones. The system chooses the most likely path. But probability, as Loschmidt noted, is blind to direction. If we reverse all velocities, the molecules should obey the same arithmetic and climb downward in entropy instead of upward. The dice do not know whether we have flipped the table. The paradox is simple to state, devastating in implication. If the micro laws are symmetric, why should the macro laws display a symmetry? The answer often offered is this: reversals are possible, but require an impossibly precise setup. To reverse the shattered glass, one would have to manipulate every fragment, every dust particle, every photon of light scattering from the scene, aligning them all in a grand conspiracy. It is not forbidden, It is inconceivably unlikely. Entropy grows because aligning the universe into a perfect reversal is as improbable as gathering every grain of sand on Earth into the same corner of a beach by accident. But Loschmidt's point lingers. If improbability explains the asymmetry, then the asymmetry is not truly in the laws themselves. It is in the conditions. Something must have set the universe on a track that favors one direction over another. Philosophers call this the tension between micro-reversibility and macro-r-reversibility. At the micro level, the billiard balls colliding, the electrons orbiting, the equations do not privilege forward or backward. At the macro level, the ice melting, the tea cooling, the privilege is absolute. Reconciling the two is like reconciling a mirror that reflects symmetry with a world that refuses to obey it. We are left to suspect that the arrow of time emerges not from the laws, but from the boundary conditions of the universe itself. That is, from the way the cosmic film reel began. The paradox is more than academic. It gnaws at the root of experience. If the laws are time-symmetric, then in principle we should have no reason to believe the past is more real than the future. Yet our memories, our identities, even our griefs and hopes, are tied to a world in which past and future are not equal. We know the egg will crack, but never uncrack. We can remember yesterday, but not tomorrow. Loschmidt's paradox presses the question, is our arrow of time an illusion generated by statistics, or is it a feature of the universe's very foundation? Consider again a box of gas molecules. At any instant, one could record every position and every velocity. Reverse them all, and the molecules would retrace their history, clustering neatly into their earlier state. The second law would appear violated, entropy falling. But to perform that reversal is to demand a godlike control beyond possibility. A single deviation, one atom misaligned, and the system collapses back into disorder. That fragility is why the arrow holds in practice. Yet the fact remains. The equations do not forbid the reversal. They remain silent, impartial, while our world insists on only one choice. This silence has drawn many interpretations. Some argue that the arrow is not fundamental at all, but emergent, a large-scale illusion. At the smallest scales, time is symmetrical. It is only when we group countless particles together that a symmetry appears. Others propose that quantum mechanics holds the secret, that the collapse of wave functions introduces an irreducible one-way process. Still others look to cosmology, suggesting that the Big Bang's low entropy is the true source of the arrow. Loschmidt's paradox hovers over each theory, reminding us that any explanation must reconcile reversible equations with irreversible reality. Boltzmann, challenged by Loschmidt, defended his position with passion. He argued that while reversals are possible in principle, they are irrelevant in practice. The sheer scale of improbabilities is enough to guarantee that entropy almost never decreases. In this sense, the second law is like the inevitability of waves smoothing the beach. Not impossible to resist, but overwhelming in likelihood. Yet the debate left scars. Boltzmann would die before the 20th century began, his epitaph carved with the formula for entropy. Loschmidt lived longer, but his question outlived them both. To this day, physicists and philosophers still wrestle with it, finding in the paradox not just a technical puzzle, but a window into the essence of time. What does it mean, then, to live inside Loschmidt's paradox? It means inhabiting a universe where the laws whisper symmetry, while our lives sing asymmetry. It means reconciling the mathematics of possibility with the lived certainty of irreversibility. It means knowing that the arrow of time is at once fragile in theory and absolute in practice. Every broken plate, every extinguished flame, every memory etched in neurons is a testament to the paradox unresolved. And so, the broken clock remains a witness not just to entropy, but to the deeper contradiction. Its hands once moved under the symmetry of mechanics, yet they tell us of a world that cannot rewind. The paradox sharpens the mystery rather than resolves it. If time is symmetric in principle, but asymmetric in fact, then perhaps the arrow is a bridge between the world, as equations describe it, and the world as we experience it. To walk across that bridge is to confront the enigma that Loschmidt laid bare. The heart of time beats with a contradiction, and that contradiction is what makes the arrow pierce so deeply into our existence. Close your eyes and summon a memory. Perhaps it is the taste of tea this morning, or the sound of rain last night, or the face of a friend seen years ago. Each recollection points behind you, into what has already unfolded. You can recall yesterday with effort, but you cannot summon tomorrow. No matter how hard you strain, no vision of the future comes with the same solidity. At best, you can imagine possibilities, predictions, guesses, but these are phantoms, not memories. This asymmetry, the one-way nature of memory, is the psychological arrow of time. It binds the mind to the same current that entropy carries through the physical world. The brain is not a neutral recorder. Inside its tissue, cells fire in intricate patterns, weaving experiences into networks of association. The hippocampus, nestled deep within, is the organ of memory consolidation. It does not record every detail, but builds a scaffold of what was important, stitching fragments into coherent narratives. Neurons strengthen their connections through synaptic plasticity, embedding the past in patterns of activity that can be reawakened later. But this machinery works in only one direction. It encodes what has been, not what will be. There is no neurobiological mechanism for pre-coding the future, because the future has not yet delivered signals for the neurons to etch. The asymmetry is not a philosophical curiosity. It is written into the biology of memory. And so, each morning when we awaken into a world already half-shaped. We carry traces of days gone by, but no traces of days yet to come. The difference is not subtle. It is the foundation of identity. You are the same person today as yesterday, because your memories bind you to that continuity. Without them, you would dissolve into a sequence of disconnected presents. The arrow of time is not just out there in the cosmos, written in entropy and expansion. It is also in here, in the theater of the mind, where we are condemned to remember only one direction. Psychologists and neuroscientists have studied the mechanics of this arrow with fascination. Memory is selective, fallible, mutable, but it never runs forward. Even false memories, invented and inserted, are oriented backward. We fabricate pasts, not futures. The stories we tell ourselves are always anchored in what has supposedly already happened. The imagination of what lies ahead is a different faculty altogether. Planning, projecting, simulating. It may borrow pieces of memory, recombine them, and sketch a possible tomorrow. But this is not remembering. It is rehearsal, a creative guess. The certainty of memory and the uncertainty of prediction mark the border between past and future. The brain itself lives within the arrow. Why should this be so? One answer is that memory evolved as a survival tool, to learn from what has worked or failed, to avoid dangers encountered before, to repeat successes. These require recall of the past. Evolution has no need for a faculty to remember the future, for the future is not yet written in the material of the world. It unfolds as entropy increases, as causes lead to effects. A memory of tomorrow would be nonsense, like recalling a page that has not yet been printed. The arrow of time dictates that information about the future is unavailable until the future becomes present. Thus, memory is asymmetrical because reality is asymmetrical. There are, of course, experiences that blur this line. Déjà vu feels like remembering the present, as if one has already lived it. Dreams sometimes offer visions that resemble events yet to occur, though these are usually the brain recombining fragments of the past into convincing illusions. The prophetic feeling is powerful, but when examined closely, it reduces to coincidence and selective recall. The arrow is never truly reversed. Even in dreams, what seems like future memory is only the recycling of past fragments under the cover of night. This connection between entropy and memory is profound. To record a memory requires energy. Neurons fire, neurotransmitters are released. Proteins reshape synapses. The brain spends calories to inscribe the past into its circuits. In doing so, it increases entropy in the larger system. Heat released, molecules scattered. Remembering is not free. It is an act of carving order locally while pushing disorder outward. Just as life builds structures against entropy by feeding on energy, so memory builds identity against forgetting by burning fuel. The arrow of entropy and the arrow of memory are entangled. From another angle, one might say that memory is the mind's witness to entropy. When milk spills, entropy rises. When you watch it and recall it later, the memory of the spill is itself another artifact of entropy rising in your brain. Both event and memory point in the same direction. That is why we never remember the future. The future has not yet generated the entropy events that our minds can encode. Only the past has left such marks. Memory is nothing more, nothing less, than the echo of entropy written into the fragile network of cells. This arrow shapes our sense of causality. We believe causes precede effects because we remember the cause but not the future effect. Strike a match. We recall the friction before the flame, not the flame before the friction. But in the equations of physics, cause and effect are less clear. The symmetry of the laws does not forbid a flame from coming first. What makes causality feel real is the orientation of memory. The psychological arrow thus underpins not only our identity, but also our logic, our reasoning, our very grip on reality. To reverse the arrow would be to collapse meaning itself. Imagine, for a moment, a creature that remembers the future instead of the past. It would wake with knowledge of events yet to come, but no knowledge of what had just transpired. It could anticipate perfectly, but could never recall. Its sense of self would unravel, unable to build continuity from one moment to the next. Such a creature might be omniscient about what lies ahead, yet unable to learn from behind. It would be trapped in a strange asymmetry, one that evolution has never produced, perhaps because the arrow of entropy forbids it. The exercise is a reminder. Memory is not arbitrary. It is aligned with the deep grain of reality. We remember the past because the past is where entropy was lower, and those low entropy states left records we can store. The future has not yet made its records. And so, the psychological arrow is not separate from the thermodynamic arrow. They are two faces of the same current. The broken clock reminds us that time does not rewind. The mind reminds us that we cannot remember backward. Entropy ensures that the future will hold more disorder than the past. The brain ensures that our sense of self flows only in one direction. Together, they weave a unity between the outer and the inner, between physics and consciousness. To live is to be carried forward not only by molecules scattering, but also by memories binding. The arrow pierces both cosmos and mind. At night, when we close our eyes, the memories of the day drift into dream. The arrow does not stop. The brain replays, reorganizes, consolidates. Even in sleep, we are remembering backward, never forward. The theater of the mind follows the same law as the theater of the world. When dawn comes, we awaken with yesterday in our pocket and tomorrow still empty, waiting to be filled. The arrow remains steady and irreversible, drawing us onward. And perhaps this is its most intimate gift, that our sense of continuity, of identity, of being someone at all, is bound to its one-way course. Without the psychological arrow, there would be no story, no self, no meaning. With it, we are being stretched between memory and possibility, anchored in the past, yet carried unceasingly toward the future. A match is struck, and then the flame appears. A stone is released, and then it falls. A seed is planted, and then the tree grows. Our lives are threaded with this sequence. Cause comes before effect. We never see the flame first and the striking second, never the tree before the seed. The conviction is so deep that it feels like an axiom of reality, a structure more fundamental than any law. But just as with memory and entropy, cause and effect may not be as absolute as we assume. They may be another manifestation of the arrow of time, born not from the raw equations of physics, but from the asymmetry of the universe. In the bare language of fundamental laws, nothing requires that causes precede effects. The equations of motion are time-symmetric. They do not prefer one order over another. If you reverse them, effects can lead into causes just as well. The ball can roll before the hand pushes it. The ripple can expand before the pebble touches the water. On paper, both sequences are admissible. Yet in the world, one sequence reigns exclusively. The reason lies in the boundary conditions, in entropy, in the way records are made. Effects leave traces in the past, but not in the future. Causes can be remembered, but future effects cannot be stored until they unfold. And so, we perceive an order, a hierarchy. The push leads to the motion, the spark leads to the fire. The arrow of causality is aligned with the arrow of entropy. To see this more clearly, think of a broken vase. Its fragments scatter across the floor. The cause, the slip of a hand, is embedded in the past. The effect, the shattering, is embedded in the present moment and remembered afterward. What we never encounter is the vase reassembling, fragments leaping together, hand closing around a restored whole. Such a reversal would require the effect to precede the cause, a violation not of the equations, but of entropy's dictate. The number of disordered states, shards across the floor, is vastly greater than the number of ordered states, a whole vase on a shelf. The probability tilts so sharply that the reverse chain is erased from experience. Cause and effect, then, are not written into the micro laws, but into the macro statistics of the universe. In philosophy, this has provoked endless debate. David Hume in the 18th century already doubted that causality was an inherent property of the world. He argued it was a habit of mind, a pattern we impose when we see one event regularly followed by another, strike after strike, flame after flame, and we infer necessity. But the inference is ours, not nature's. In modern physics, entropy gives Hume's skepticism a new frame. We experience causes leading to effects, because entropy grows and because our memories are aligned with that growth. Causality is not so much a fundamental law as a shadow cast by the arrow of time. Still, the shadow is powerful. Our entire framework of science, our reasoning, our moral systems, all rest on it. We ask, what caused this illness? What caused the galaxy to form? What causes the rain to fall? To strip causality away is to unravel the fabric of explanation. And yet, at the deepest level, causality may not be primary at all. It may be an emergent rule, as local and fragile as the order in a cup of swirling cream. This fragility is unsettling. If causality is only a byproduct of entropy, what happens in realms where entropy's arrow blurs? What happens near black holes, in quantum superpositions, or in closed time-like curves where the future loops into the past? The neat chain of cause and effect may fray, leaving us adrift. Think of an echo in a canyon. The sound you produce causes the echo, which you hear later. But in the equations, the echo is simply part of the wave propagation, no less fundamental than the initial shout. The cause is a convenient designation we impose, carving a direction into the physics. But the physics itself is a seamless whole, equally describable forward or backward. The asymmetry comes from the fact that the canyon air begins in a relatively low entropy state, able to carry the organized wave outward. Once the sound disperses, entropy rises, and there is no organized reversal. You will never hear an echo forming before you shout. Once again, entropy dictates the arrow. This connection reveals why causality feels so deeply bound to experience. Our brains are prediction engines. They use memory of the past to anticipate effects of current causes. Drop the glass, and you already anticipate the shatter. The anticipation is not certainty. It is probability informed by past experience. The brain itself evolved in a world ruled by entropy. Creatures that could predict effects from causes had an advantage. Those that could not became extinct. In this way, evolution aligned cognition with the arrow of entropy, embedding causality in our very survival. We are wired to think in causes and effects because the universe is wired to climb entropy. There are thought experiments that test this bond. Imagine a video of billiard balls colliding on a table. Played forward, the collisions look natural. Played backward, they look equally natural until the balls come to rest and suddenly leap into motion, converging into a single strike. At that moment, the reversal reveals itself. Why? Because entropy decreased. The improbable coordination of motions marks the video as backward. We recognize cause and effect not by any hidden law, but by the telltale sign of entropy's arrow. The order of causality is simply the order of entropy. Even in language, the structure of cause and effect permeates. We say because, therefore, as a result. Our stories, our histories, our laws all presuppose the arrow. Remove it, and narrative collapses. A story without causality is incoherent, a series of disconnected snapshots. That is what life would be without the arrow, a disconnected chaos, no before or after, no reason, no identity. In this sense, causality is not only a reflection of entropy, it is the human translation of entropy into meaning. The universe climbs disorder, and we call the climb cause leads to effect. The match burns, the stone falls, the tree grows. Each sequence reaffirms the asymmetry, and yet, deep in the mathematics, the equations remain impartial, allowing the flame before the strike, the effect before the cause. But the world does not. We live in the world, not on the chalkboard. And so, the arrow binds us. Entropy increases, memory looks backward, causes precede effects. These are not separate truths, but facets of one truth. The arrow of time is the parent. Causality, memory, and experience are its children. In the quiet of the evening, when one reflects on the day, the chain of causes and effects is what stitches the story together. Breakfast caused the energy for work. Work caused the fatigue for sleep. Sleep will cause tomorrow's alertness. The chain continues, unbroken, unidirectional. No link ever inverts. And in that unbroken chain, we find the structure of meaning itself. Without it, the story would dissolve into incoherence. With it, we inhabit a world where time has a direction, and we call that direction causality. Stand beneath a summer sky and feel the warmth of sunlight on your skin. Look upward, and you see clouds drifting, their edges curling into spirals, their shapes evolving from moment to moment. The atmosphere is never still. It is a restless canvas painted in motion, winds shifting, currents rising, storms gathering strength from invisible gradients of pressure and temperature. For as long as humans have looked to the heavens, we have sought to predict these motions. Farmers wanted to know when the rains would arrive. Sailors wanted to know when the storms would break. And today, with satellites and supercomputers, we still chase that desire. Yet the weather resists us, not because it is lawless, but because it is ruled by laws that are exquisitely sensitive. In the dance of clouds and winds, we encounter another face of the arrow of time, chaos and unpredictability. The atmosphere obeys equations first written down by Newton and later extended by Navier and Stokes. These equations are time-symmetric. Like the collisions of billiard balls, they do not prefer one direction. If you reverse the velocities of every air molecule, the equations would allow the system to rewind. But in practice, the weather is irreversible. Why? Because chaos magnifies tiny differences into vast divergences. A single molecule's deviation grows until it changes the trajectory of winds, alters the formation of clouds, redirects the path of storms. This is the butterfly effect, the famous metaphor offered by Edward Lorenz. The flap of a butterfly's wings in Brazil may set off a tornado in Texas. The image is poetic, but the science is precise. Weather systems are so sensitive that no measurement can capture their initial state with infinite accuracy. Entropy rises, and with it, predictability collapses. This is why forecasts extend only so far. 3 days ahead, we can say with confidence whether it will rain. 5 days ahead, the confidence fades. 10 days ahead, the forecast is little better than a guess. Beyond that horizon, chaos erases the thread of prediction. The arrow of time manifests here not as memory or causality, but as a wall against foresight. We cannot remember the future of weather because the system's entropy multiplies uncertainty until tomorrow's clouds dissolve into statistical haze. The unpredictability is not a failure of science, but an expression of the second law. Information decays, order dissolves, the arrow points forward, and our vision becomes blurred. Consider a storm forming over the ocean. Warm air rises, cools, condenses, releasing latent heat. The spiral grows, feeding on temperature gradients, twisting into a cyclone. Every step is governed by physics, pressure gradients, Coriolis, deflection, conservation of angular momentum, but the storm's exact path cannot be known far in advance. Entropy ensures that the number of possible configurations multiplies until one cannot say which shoreline will bear the brunt. The hurricane is an arrow in motion, driven by the irreversible transfer of heat from ocean to sky. Once begun, the process cannot be reversed. The sea will not grow warmer as the storm returns energy in perfect order. The storm disperses energy, scatters it, writes entropy into the air and the sea. The arrow of time is carved into the wind itself. The history of meteorology is a history of confronting this arrow. Aristotle wrote of weather as a divine mystery, his Meteorologica an attempt to catalog the caprices of the sky. Centuries later, barometers and thermometers offered instruments to measure pressure and temperature, anchoring prediction in numbers. The Beaufort scale quantified winds for sailors, transforming lore into law. By the 20th century, the equations of atmospheric dynamics were known, and with them came the dream of perfect forecasting. If only we could measure every molecule, we could calculate the future of weather precisely. But Lorenz, working with one of the earliest computers, discovered the impossibility. A tiny rounding error in his program produced forecasts that diverged wildly. From that moment, the limits of prediction were revealed. The arrow of chaos was aligned with the arrow of time. And yet, within that chaos, patterns emerge. Climate, unlike weather, is stable over decades. Seasons return, monsoons recur, jet streams carve familiar paths. The arrow of time here is not only unpredictability, but also rhythm. Time shapes the cycles of rain and drought, of storm and calm, of migration and flowering. Entropy rises in each individual event, but over the long scale, a tapestry of recurrence is woven. The paradox is that order emerges from disorder, but only when averaged across vast ensembles. The daily weather defies prediction beyond days, but the climate whispers probabilities across centuries. This too is the arrow of time, the short-term chaos and the long-term pattern. The unpredictability horizon is not confined to meteorology. It echoes across all chaotic systems, the rolling of dice, the eddies of rivers, the orbits of planets in crowded systems. Each obeys symmetric laws, yet displays irreversible unpredictability. Entropy ensures that while the laws are reversible, the information is not. Once initial conditions blur, they cannot be sharpened. The film cannot be rewound. The clouds cannot reassemble. The arrow points inexorably forward. But weather carries a special intimacy. It is the arrow we feel on our skin, the entropy we hear in the roar of storms. We live beneath the sky, vulnerable to its moods, humbled by its unpredictability. A forecast delayed or wrong reminds us that not even supercomputers can defy the arrow. Chaos rules the atmosphere, and entropy rules chaos. The storm that wipes away a coastline is not just a meteorological event, but a message. Time moves forward, order dissolves, predictions fail, and we are swept along. At night, when the wind howls outside the window, one might imagine reversing the storm, clouds unraveling into blue, winds calming into stillness, waves retreating into sea. The equations might allow it, but reality does not. The entropy written into the storm forbids the reversal. The howl is the voice of the arrow, reminding us that the sky itself is bound to time's one-way march. And when the storm passes, leaving wreckage behind, the asymmetry is undeniable. The broken houses will not rebuild themselves. The calm after the storm is not the reverse of the storm, but its consequence. Cause and effect, entropy and unpredictability, chaos and irreversibility, all are bound together in the weather's restless flow. Thus, the arrow of time is not only in the shattering of glass or the fading of memory. It is in the winds that carry clouds, in the storms that gather strength, in the limits of our ability to see beyond the horizon of prediction. Every forecast is a wager against entropy, every model a temporary defiance, but beyond a certain span, the arrow wins. The horizon of chaos closes, and the future dissolves into probabilities. That is the law of the sky, and it is the law of time itself. The story of time's arrow leads inevitably backward, not just to childhood memories or the early days of Earth, but to the beginning of everything. If entropy increases, then yesterday was lower than today, and the day before, lower still. Trace this logic far enough, and we arrive at the first dawn, the Big Bang. Yet here we meet a mystery more profound than shattered vases or cooling tea. For when the universe was born, it emerged in a state of astonishing order, an entropy so low that all the disorder since then has been only a climb up its slope. Why the beginning was so improbably neat remains one of the greatest unanswered questions in physics. To appreciate the strangeness, imagine a vast library. Most of the books are scattered, their pages torn, their order ruined. A few are shelved neatly. Entropy tells us that systems tend to move from the rare shelves of order into the vast wilderness of disorder. The Big Bang, by this analogy, was a library in which every book stood perfectly upright, every page aligned, every word in place. In probabilities language, this is almost impossible, yet it happened. The universe began not in chaos, but in startling order. Without that order, the arrow of time would have no slope to climb. If the beginning had already been maximum entropy, there would be no unfolding, no future, no history, only stasis. Boltzmann wrestled with this puzzle. His statistical mechanics explained why entropy tends to increase, but not why it was ever low in the first place. Some of his followers speculated that perhaps the universe is infinite and eternal, and what we call the Big Bang was simply a fluctuation, a rare pocket of low entropy that appeared by chance. In this picture, order arises occasionally out of chaos, like a perfectly shuffled deck appearing once in unimaginable time. But this explanation, though ingenious, raises its own problems. If fluctuations can produce ordered pockets, then it is far more probable to produce small ordered illusions, like a single brain with false memories of a universe, than an entire cosmos. These hypothetical Boltzmann brains are more likely than universes, and yet we are not isolated brains adrift in chaos. The fact of our existence suggests that the fluctuation idea cannot be the full story. Other physicists have turned to gravity. Entropy in ordinary matter is about scattering and mixing, but entropy in gravitational systems behaves differently. A cloud of gas dispersed evenly through space might look like maximum entropy, but under gravity it is unstable. Clumps form, stars ignite, galaxies swirl. Perhaps the early universe's low entropy is explained by gravity's peculiar role. The smoothness of the primordial cosmos was in fact the most ordered state possible, setting the stage for later clumping and structure. In this view, the low entropy of the beginning is less improbable than it seems. It is simply the baseline from which gravitational complexity could arise. And yet the riddle persists. Why was the early universe so smooth? Why not already filled with black holes, the ultimate high-entropy objects? Why not born in chaos? Roger Penrose, one of the great explorers of space-time, argued that the smoothness of the cosmic microwave background, the relic radiation from 380,000 years after the Big Bang, is evidence of an exquisitely low-entropy past. He calculated the improbability of such order as 1 in 10 moides 10 123, a number so vast that it defies imagination. To put it in perspective, if every atom in the universe were marked with a unique label, and you searched for one special atom, your odds would still be infinitely better than the odds of hitting that exact low-entropy configuration by chance. The birth of the cosmos was, by all our measures, improbably pristine. This low-entropy origin is the fountain from which time's arrow flows. Because the universe began in such an ordered state, every subsequent moment has been a step toward greater disorder. Stars ignite and burn their fuel. Galaxies merge. Planets cool. Life arises as a temporary pocket of order, at the cost of exporting entropy outward. History itself is the blossoming of entropy from an improbably low seed. If the seed had not been low, the arrow would never have sprouted. The fact that we remember the past, that milk spills but does not unspill, that weather resists prediction, that causes precede effects, all these depend on the beginning's order. The arrow of time is a legacy of the Big Bang's initial condition. Some cosmologists speculate that the explanation may lie in deeper laws we have not yet uncovered. Perhaps the multiverse, an ensemble of universes beyond our own, generates countless births, and ours happen to be among the rare few that began ordered. Perhaps there is a principle of cosmic selection that favors low entropy at birth. Perhaps time itself is emergent, and the very concept of low-entropy beginning is only a byproduct of how consciousness samples reality. Each proposal is daring, and none is proven. What is certain is that the arrow of time cannot be separated from the mystery of origins. To understand one is to confront the other. This mystery is not abstract. It reaches into every breath we take, the oxygen we inhale, the neurons that fire to shape memory, the star that burned long ago to forge the elements in our blood. All of it is possible only because the early universe was smooth and low in entropy. We are descendants of that improbability, children of an ordered beginning. Our lives, with their stories and struggles, are the unfolding of a cosmic asymmetry set billions of years ago. When we gaze into the night sky and see the faint afterglow of the Big Bang in the microwave background, we are looking at the frozen signature of that order. It is a whisper from the beginning, telling us that the arrow began with a single, improbable stroke. At the end of the day, as entropy continues its climb, we return to the paradox. If the laws are symmetric, why was the beginning asymmetric? If entropy tends to increase, why was it ever low? The arrow of time is undeniable, yet its root is still obscure. The Big Bang gave us a universe capable of history, of memory, of meaning. But why it gave us that and not eternal stasis remains unsolved. Perhaps it always will. Perhaps the arrow is less a riddle to be answered than a gift to be lived. For without it, there would be no past to remember, no future to imagine, no selves to carry between. The low entropy of the beginning is the silent stage on which every story, yours and mine, is performed. The night sky is not still. Though it seems eternal to the naked eye, every star is rushing away from us, every galaxy retreating. the very fabric of space stretching. Edwin Hubble's discovery in the 1920s transformed our picture of the cosmos. The universe is expanding. And with this expansion came a new arrow, one that runs parallel to entropy and causality, the cosmological arrow of time. Just as a balloon inflates and every point on its surface drifts apart from every other, so the universe itself grows larger with each passing second. The direction of that growth has never reversed. The arrow points outward, away from the beginning, and it has done so for nearly 14 billion years. This expansion is not a small detail. It is the condition that makes everything else possible. In the early universe, matter and energy were compressed into a nearly uniform state, hot and dense beyond imagination. As the universe expanded, it cooled. Expansion allowed structures to form, galaxies, stars, planets, and eventually, life. Without the expansion, the cosmos would have remained a smooth soup of radiation. No clumps, no complexity, no story. The arrow of time is stitched into the expansion. Past means smaller and hotter. Future means larger and colder. That simple correlation defines the cosmic direction. And yet, expansion itself is governed by equations that are, once again, reversible. General relativity, Einstein's great theory of space-time, admits solutions where the universe contracts as well as expands. In principle, time could run toward a big crunch just as easily as toward eternal expansion. But the reality we inhabit has chosen one side. The arrow points to growth, not shrinkage. If you reverse the film of cosmic history, galaxies converge, stars collide, temperatures soar, and the universe compresses. But that reel is not the one playing. The entropy of the cosmos is rising as it expands, and so the cosmological arrow is aligned with the thermodynamic one. The outward breath of the universe is also the forward motion of time. The link between entropy and expansion is subtle. In a contracting universe, entropy would still rise. Stars would still burn, glasses would still shatter, milk would still spill. But the global direction would look different. A universe collapsing toward a big crunch might still contain beings like us, but their sense of time would be peculiar. Would they remember the contraction as moving forward? Would they imagine their arrow pointing toward the crunch? These questions remain speculative, but they remind us that the arrow is not only local, but cosmic. The universe as a whole has a direction, and we are caught in its stream. Dark energy complicates the picture. In the late 20th century, astronomers discovered that the universe is not only expanding, but accelerating. Space itself is stretching faster and faster, driven by a mysterious energy we do not yet understand. This acceleration means the arrow may never reverse. The dream of a big crunch recedes. Instead, we face a long future of dilution. Galaxies rushing beyond each other's horizons, stars burning out, matter decaying into darkness. The expansion writes a future of isolation. Each observer will someday see nothing but the faint light of their own galaxy. The rest of the universe vanished beyond reach. The cosmological arrow is not only expansion, but separation, the fading of cosmic companionship. Time points not only outward, but toward loneliness. Yet the cosmological arrow is also the reason we can trace history. The cosmic microwave background, the afterglow of the Big Bang, is stretched light. Its wavelength has been elongated by expansion from a blazing radiation to a cool microwave hum. That hum fills the universe today, a faint echo of its youth. Without expansion, there would be no record of beginnings. The arrow gives us not just a future, but a past, an ability to look backward across billions of years. The very fact that we can reconstruct cosmic history, that telescopes can see galaxies as they were billions of years ago, is a consequence of expansion. The arrow is inscribed in starlight. There is a haunting question. What if the expansion were to stop, to reverse? What if gravity one day overwhelmed dark energy, drawing the universe back into a collapse? Would the arrow of time itself reverse? Would entropy begin to decrease? Memories run backward? Effects precede causes? Some thinkers have entertained this possibility, but most argue that entropy would continue to increase even during contraction. The arrow would persist, though its scenery would change. Instead of galaxies racing apart, they would converge. Instead of cooling, the universe would heat. But the direction of time, the march of entropy, would remain. Reversal is not escape. The arrow does not bend backward. It only changes what lies ahead. The expansion also invites metaphors, a loaf of raisin bread rising in the oven. Each raisin drifts away from the others as the dough expands. None is privileged as the center. All move apart. The universe is the dough, galaxies the raisins. Or a balloon inflating. Each point on the surface recedes from every other. These metaphors are simple, almost childlike, yet they convey the grandeur of the arrow. The expansion is not an explosion in space. It is space itself, stretching, carrying everything with it. Past is smaller, future is larger. That is the cosmological rhythm. We live in a moment balanced between origin and fate. The universe has expanded for billions of years, but not yet so much that the night sky is empty. We can still see distant galaxies, still detect the ancient background light, still measure the expansion itself. But we know this moment is temporary. The arrow carries us toward a different vista, one where the stars thin and the sky darkens. The expansion is not just an arrow, it is a promise and a warning. It promises that the cosmos has a history, a direction, a story. It warns that the story is moving inevitably toward a state we cannot escape. In the quiet of the night, look up and imagine the galaxies receding. Each point of light is a memory, a fragment of an earlier chapter. To see them is to look backward in time, to witness the arrow etched across billions of years. The expansion is not an abstraction. It is visible in every telescope, audible in the microwave background, felt in the inevitability of cosmic cooling. It is the breath of time itself, expanding outward, carrying us along. And so, the cosmological arrow joins the others. Entropy increases, memory looks back, causes precede effects, and the universe itself grows larger, never smaller. The arrows align, weaving together into one irresistible current. That current is time. To deny it is impossible. To escape it is inconceivable. We live within the outward breath of the cosmos, children of its expansion, passengers on its irreversible voyage. The arrow of time is written not only in broken glasses and fading memories, but in the galaxies themselves, receding into the dark. In 1905, Einstein revealed that time was not absolute. Special relativity showed that clocks tick differently depending on their motion, that simultaneity is not universal, that space and time fuse into space-time. Later, with general relativity, he wove gravity into the very geometry of that space-time. Out of these theories emerged a picture that unsettled intuition: the block universe. In this view, past, present, and future are all equally real. The cosmos is a four-dimensional block where every event, your birth, this sentence, the last flicker of the final star, is frozen, laid out as a landscape. Time, in this picture, does not flow, it simply is. We do not move through time any more than a traveler moves through longitude. The arrow is absent, or at least hidden, in the geometry of space-time. Einstein himself leaned toward this interpretation. In letters near the end of his life, he consoled a friend who had lost a loved one by writing that, for those of us who believe in physics, the separation between past, present, and future is only a stubborn illusion. The words strike like cold water. If the block universe is true, then our sense of becoming, of unfolding, of a moment passing into the next, is not fundamental. It is a trick of perception. Time does not march. It already exists, all of it, in one eternal tableau. What we call the present is simply the point our consciousness inhabits, sliding along a pre-existing track. This vision is breathtaking and disturbing. It robs us of the idea of openness, of possibility. If the future already exists, are we truly free? If tomorrow is as real as yesterday, then the arrow of time is no arrow at all, only a perspective. The block universe erases the flow, turning the river into an ice sculpture. And yet, it fits perfectly with relativity's equations. Nothing in Einstein's space-time privileges one moment over another. The geometry is indifferent. The laws are timeless. The arrow that feels so undeniable in our lives evaporates into illusion. But the illusion refuses to go quietly. For even if the block exists, why do we perceive the flow? Why do we experience one frame of the block after another, never skipping, never reversing? The block may contain all events, but our consciousness seems to move along them. The question is whether this movement is real or only apparent. Some physicists argue that the block universe is compatible with the arrow of time because entropy is unevenly distributed across the block. The low entropy of the Big Bang marks one end, higher entropy marks the other. Our consciousness is aligned with that gradient, so as we move through the block, we feel time's arrow, Others reject this, insisting that the flow is irreducible, that the block picture is incomplete. There is also a haunting irony. Relativity, in erasing the universal present, leaves each observer with their own slice of now. What is now for you may not be now for someone moving at a different speed. The present is fractured, relative, dependent on perspective, and yet each observer still feels the arrow. Everyone, regardless of motion, remembers the past and not the future. Everyone feels entropy increase in the same direction. So, while relativity dethrones the present, entropy restores it, giving all observers a shared orientation. The block universe may flatten time, but entropy lifts one edge higher than the other, creating a slope we cannot ignore. Philosophers have wrestled with this paradox for centuries. The eternalists embrace the block, declaring that past and future are as real as the present. The presentists resist, insisting that only the present truly exists. Between them lies the growing block theory, where the past and present are real, but the future is not yet. Each view attempts to reconcile the symmetry of physics with the asymmetry of experience. None has resolved the tension fully. The block is elegant. The flow is undeniable. We stand between them, pulled by equations to one side and by consciousness to the other. One way to soften the paradox is to imagine the block as a book. The pages are all there, bound from first to last, but the story is revealed only as we read it. The book does not change, but our reading gives it life. The arrow of time is our reading order, imposed on an already written narrative. This metaphor comforts, but it also sharpens the unease. If the story is already written, are we free to choose? Or are we characters who believe in choice while following a fixed script? The block universe raises not only scientific questions, but existential ones. It touches free will, identity, meaning. And yet, perhaps the metaphor misleads. For while the block suggests stasis, the universe is not static in our perception. Entropy grows, records accumulate, memories stack. The very act of consciousness seems tied to the production of information, which requires a direction. If the block contains all times, then entropy must be inscribed unevenly across it. The Big Bang's low entropy anchors one end. The heat death anchors the other. Between them stretches the slope, and we are beads sliding down it. The block is not featureless. It is tilted, textured, patterned by entropy's gradient. In that gradient, the arrow finds a home. Still, the tension remains unresolved. Einstein's block strips away the flow. Our lives insist on it. Physics speaks of symmetry. Experience sings asymmetry. Which is fundamental? Perhaps both. Perhaps the block is the map, and the arrow is the journey. The map contains every road, every town, every destination, already drawn, but the journey is lived step by step, with memory of where we have been and anticipation of where we are going. The block is the geometry. The arrow is the story. Neither cancels the other, but neither can be reduced to the other. Late at night, one might wonder. If the block is real, then this moment has always existed and always will. Your eyes moving across these words, your breath rising and falling, your heart pulsing with time, these are not fleeting, but eternal, frozen into the structure of space-time. And yet, you feel them pass. You know the next breath will come, the next heartbeat will follow, the next word will arrive. The flow is undeniable, even if the block denies it. This is the paradox we inhabit, beings of flow in a universe of geometry, creatures of arrow in a cosmos of symmetry. Perhaps the arrow of time is the price of consciousness. Without the sense of flow, without the alignment of memory and entropy, we could not have selves, stories, or meaning. The block may exist, timeless and complete, but the arrow is what makes it inhabitable. It is the difference between a frozen sculpture and a living journey. The equations describe the sculpture. Our lives embody the journey. Between them lies the mystery of time, a mystery that Einstein unveiled but never fully explained. The arrow remains, piercing even the block, carrying us onward through a universe that is both eternal and fleeting, both fixed and flowing. At the scale of atoms and electrons, the universe begins to feel slippery. Classical certainty gives way to quantum possibility. An electron is not in one place but in many, its position smeared into a probability cloud. A photon is not simply a particle of light, but a wave spread across paths. Before measurement, the quantum world is described by a wave function, a shimmering superposition of all that might be. Then, at the moment of observation, the wave function collapses into one reality. The electron is here, not there. The photon has taken this path, not that. In this collapse, many physicists see the whisper of an arrow of time. For the Schrödinger equation, which governs quantum evolution, is perfectly reversible. The wave function spreads forward or backward in time with equal indifference. Reverse the sequence, and the mathematics is unchanged. In this realm, time has no preferred direction. But measurement, the act of extracting a definite outcome, seems to break the symmetry. Collapse is irreversible. Once the wave function has chosen, there is no going back. We never see a measurement that undoes itself, restoring the superposition. The arrow appears in the gap between the timeless equations and the irreversible act of observation. This is the paradox at the heart of quantum mechanics. The equations tell one story, our experiences tell another. We build detectors, fire photons, record clicks, and those records point in only one direction. The film never runs backward. But if collapse is fundamental, if it is built into the fabric of the universe, then perhaps the arrow of time is too. The universe itself may be making choices, and each choice is a cut in possibility that cannot be mended. Entropy grows not only in spilled milk and shattered glasses, but in wave functions that narrow into facts. But not all physicists agree that collapse is real. The Copenhagen interpretation holds that measurement collapses the wave function, but others argue this is only an appearance. The many worlds interpretation insists that no collapse occurs. Instead, the universe splits. Every possibility realized in parallel branches. In such a picture, the arrow of time is not born from collapse, but from decoherence. Quantum systems, when entangled with their environments, lose their delicate interference. Superpositions blur into classical outcomes because information disperses into countless degrees of freedom. Decoherence is itself irreversible. The branches never recombine. Entropy increases and the arrow persists. Collapse or no collapse, the quantum world resists reversal. Still, measurement holds a peculiar place in our intuition. To watch is to force choice. The cat in Schrödinger's box is alive and dead in superposition until the lid is lifted. And then it is only one. No observer has ever watched the cat return to superposition after being observed. The arrow of time is stitched into the very act of looking. Our minds, our instruments, our notebooks, all record the outcome in one direction. To unrecord would mean erasing not only ink, but memory. Not only memory, but entropy itself. The quantum arrow is therefore entangled with the psychological and the thermodynamic. They are not separate, but mirrors of each other. There is an elegance here, though it is tinged with unease. If the arrow is tied to measurement, then the universe itself is a kind of observer. Every interaction, every atom bumping another, every photon striking a surface, acts as a measurement. Each narrows possibilities into outcomes. The cosmos is constantly collapsing its wave functions, continually writing facts into being, continually increasing entropy. Reality is the story of these choices, and the arrow is the sequence in which they unfold. The future remains a superposition, the past a record, the present the knife-edge collapse. We stand forever at that knife edge, carried along by the quantum current. And yet, questions multiply. If the equations are symmetric, why does measurement feel asymmetric? If collapse is real, what mechanism drives it? And why does it not run in reverse? If collapse is only apparent, why do we never see recoherence, the superpositions reforming? Each interpretation of quantum mechanics wrestles with the arrow. The Copenhagen school embeds irreversibility in collapse itself. The many-world school embeds it in the branching that cannot recombine. Objective collapse theories, like those of Gherardi and Pearl, attempt to modify the equations to include true one-way processes. Decoherence theorists argue that irreversibility emerges from entanglement with the environment. In each case, entropy plays its role, smuggling the arrow into the quantum stage. Perhaps the clearest clue is information. When a quantum measurement occurs, information is created and stored. The detector clicks, the atom recoils, the record is written. That information cannot be uncreated without dispersing it into heat, into chaos, into entropy. In this sense, the arrow is less about collapse than about information flow. Quantum systems may be reversible in theory, but once they touch the macroscopic world, information bleeds irreversibly outward. Like ink on paper, it cannot be drawn back into the pen. The universe is an ever-growing ledger of facts, each fact a marker of time's one-way march. The tension between timeless equations and irreversible outcomes is not unlike the tension between Einstein's block universe and our felt flow. On one level, everything is symmetrical, frozen, reversible. On another, everything is directional, flowing, irreversible. The arrow seems to arise at the seam where description meets experience, where equations meet records, where probability meets choice. The quantum arrow may be the most intimate, for it touches not only physics but consciousness. Our act of observing is itself part of the story. We are not outside the experiment, we are participants. Our memories are the records of collapse. Our identities are shaped by what has been chosen. To be conscious is to ride the quantum arrow. There are experiments probing these mysteries, delicate attempts to catch the wave function in the act of collapse. Weak measurements, quantum erasers, delayed choice experiments, all reveal that the line between past and future is thinner than we imagine. Photons seem to decide their behavior retroactively, depending on whether we choose to observe them. Superpositions seem to persist longer than expected, blurring the boundary between quantum possibility and classical fact. And yet, in every case, the final record is irreversible. The arrow is never broken. Whatever paradox the experiments reveal, the outcome is always one way. We never record the future, only the past. We never see entropy fall. The arrow is resilient, unyielding, even in the most delicate shadows of quantum mechanics. So, the mystery endures. The laws are reversible, but the world is not. The wave function evolves symmetrically, but the measurement does not. Collapse may be real or illusory, but either way, the arrow persists. Perhaps time's direction is woven into the very act of existence. Perhaps it is less a law than a habit of reality, a rhythm that cannot be undone. Whatever the answer, the quantum arrow joins the others. Entropy rises, memory looks back, causes precede effects. Galaxies expand, and in the trembling probabilities of electrons and photons, the wave function collapses, always forward, never back. The arrow pierces even the smallest scales, and from there, it pierces us. At the edges of the universe's imagination lie black holes, those regions where gravity becomes so intense that not even light can escape. They are the most extreme objects in nature, born from the collapse of massive stars, or from the slow merging of galaxies. To fall into one is to cross a boundary, the event horizon, beyond which return is impossible. In this sense, black holes are not only astronomical objects, but metaphors for time's arrow. They swallow, but they never give back. They represent irreversibility on a cosmic scale. The paradox begins with information. In physics, information is not a trivial thing. It is the set of distinctions that describe a system, the arrangement of atoms in a glass, the sequence of cards in a deck, the spin of an electron. The second law tells us that information disperses. Order dissolves into disorder. Detail fades into entropy. But information is never supposed to be destroyed. Even as entropy rises, the underlying information is preserved in principle. If one knew every microscopic detail, one could, at least theoretically, reconstruct the past. The arrow of time does not erase, it only scatters. But black holes appear to break this rule. When matter falls into a black hole, its information seems lost. All that remains to describe the hole are three simple numbers: its mass, its charge, and its spin. This is the no-hair theorem. The complex details of what fell in, whether it was a star, a planet, a library of books, or a living being, are obliterated. The black hole forgets. Entropy here reaches its most extreme expression, reducing countless configurations to a few bland parameters. It is as if time's arrow sharpens into a knife, cutting away the records of reality. Stephen Hawking deepened the paradox in the 1970s. He discovered that black holes are not entirely black. Quantum effects near the event horizon cause them to emit radiation, now known as Hawking radiation. Over immense spans of time, black holes evaporate, leaking their mass away until they vanish. But the radiation is thermal, featureless, carrying no trace of what fell in. If the black hole evaporates completely, the information it contains seems gone forever. This outcome would violate a central principle of quantum mechanics: unitarity, the rule that evolution is reversible and information is preserved. The paradox is stark. The arrow of time is expected, but total erasure is forbidden. Black holes seem to demand both. The information paradox has haunted physics for decades. It is a collision of arrows: the thermodynamic arrow, which insists on irreversibility, the quantum arrow, which insists on reversibility, and the cosmological arrow, which frames black holes as permanent sinks. Reconciling them has driven some of the deepest advances in theoretical physics. The holographic principle emerged as one possible resolution. Inspired by black hole entropy, Gerard 't Hooft and Leonard Susskind proposed that the information of a volume of space can be encoded on its boundary, much like a hologram stores three-dimensional images on a two-dimensional surface. In this view, the information that falls into a black hole is not destroyed, but smeared across the event horizon, encoded in its surface area. The arrow of time still drives the whole toward evaporation, but the ledger of information remains intact, written in horizon bits. The entropy of a black hole is proportional not to its volume, but to the area of its horizon. This was one of the most astonishing insights of modern physics. A black hole is the most entropic object in the universe, containing more entropy per volume than anything else. In a sense, it is the ultimate memory bank, though a strange one. The more it forgets details, the more its entropy grows. The arrow here is sharpened to its extreme. Entropy increases not by dispersing matter into space, but by compressing information onto a surface, a paradoxical twist of geometry and thermodynamics. The black hole is time's arrow folded inward. And yet, the paradox is not fully resolved. Does Hawking radiation somehow carry subtle correlations, enough to preserve information after all? Some physicists believe so, arguing that the radiation is not truly random, but entangled with the interior of the black hole. Others propose that wormholes or quantum entanglement weave connections that prevent information loss. The most radical proposal suggests that space-time itself is emergent from information, that the fabric of reality is built from entanglement, and that black holes are keys to decoding this hidden architecture. In each theory, the arrow of time plays a central role, for the flow of information, whether lost, preserved, or scrambled, is a measure of time's irreversibility. There is something poetic in this struggle. At the heart of entropy is the question of memory. Entropy rises when information is dispersed, when detail is erased, when records are overwritten. Black holes, the most extreme entropy machines, dramatize this process at cosmic scale. They consume stars and erase their stories. They swallow galaxies and compress their histories into silence. They are the graveyards of causality, where the chain of cause and effect appears to terminate. And yet, paradoxically, they may also be the guardians of information, storing it in ways we cannot yet decipher. The arrow of time, rather than ending at the event horizon, may be written most vividly there. Imagine standing near the horizon of a black hole, watching a companion fall in. To you, time seems to slow for them, their descent stretched infinitely, frozen at the edge. To them, time continues, carrying them across the boundary without return. This relativity of time deepens the symbolism. The arrow points differently depending on where you stand, but in both perspectives, it never reverses. To the falling traveler, the horizon is crossed forever. To the outside observer, the image fades, information smeared thin across the horizon. The arrow insists on one-way passage, but its story is told differently from different vantage points. The paradox is not just physical, but perspectival. In the end, black holes are reminders that the arrow of time is not simple. It is not only the spreading of gas, the cooling of tea, the fading of memory. It is also the swallowing of information, the encoding of entropy on horizons, the evaporation of cosmic giants into silence. They are both destroyers and archivists, both violators and preservers. The paradox of information loss is still unresolved, but in the very attempt to resolve it, physics has glimpsed deeper truths, that space-time and information may be two sides of the same coin, that entropy may be the fundamental currency of the universe, and that the arrow of time may be woven into the very logic of existence. To look at a black hole, even only in imagination, is to stare at a clock without hands. Time does not tick there as it does here. It folds, stretches, and ends. But the arrow is not absent. It is intensified. Whatever crosses the horizon does not return. Whatever information is stored will never emerge in familiar form. The black hole is the universe's most emphatic statement that the past and the future are not the same. The arrow of time plunges inward, never outward, and in its plunge, it writes the deepest mystery of physics, whether time truly destroys or whether, in some hidden language, it remembers everything forever. By now the arrows have multiplied. At first it seemed there was only one, the familiar march of disorder, entropy rising in broken vases and cooling tea. But step by step, layer by layer, other arrows emerged. The thermodynamic arrow, the cosmological arrow, the quantum arrow, the psychological arrow, the causal arrow, all pointing forward, never back. Each arrow seems distinct, born from different domains of reality, yet they refuse to scatter apart. Instead, they align like vectors in a single direction. The question is whether this alignment is coincidence or necessity. Is there truly one arrow expressed in many dialects? Or are there multiple arrows woven together into a single fabric? The thermodynamic arrow is the most immediate. It is the law that entropy increases, the statistical certainty that systems wander toward disorder. It is the reason milk spills and does not reassemble, the reason the universe is fated for heat death. But the thermodynamic arrow does not live alone. It is anchored by the cosmological arrow, the expansion of the universe. For without expansion, entropy might have reached equilibrium long ago, leaving no gradient to climb. The low entropy of the Big Bang and the outward breath of space gave entropy a slope, a ladder to ascend. The thermodynamic arrow is powered by the cosmological one, the way a river's current is fed by gravity's pull. Together, they define the large-scale flow. Past is small and ordered, future is vast and disordered. Then comes the psychological arrow, woven into our neurons. We remember the past, but never the future. Our identities are built from memory, our logic from causality, our sense of self from continuity. This arrow is not arbitrary. It leans on entropy's increase. Memories are traces written in low entropy states, records preserved in matter, patterns inscribed in neurons. The future leaves no records because it has not yet unfolded. Thus our minds align with entropy's direction, tethering consciousness to the universal current. We are creatures of memory because the universe itself is a creature of entropy. The psychological arrow is not separate. It is entropy refracted through biology. The causal arrow is the skeleton of narrative. Causes precede effects. Sparks precede fire. Seeds precede trees. We cannot imagine it otherwise without tearing the fabric of meaning. Yet, at the level of fundamental equations, causality is absent. Physics does not demand that causes come before effects. The ordering emerges because entropy selects it. A vase shatters because there are many more states of fragments than of wholeness, and so the chain of cause and effect is constructed in that direction. We believe in causality because the universe walks downhill in entropy. The causal arrow is entropy given structure, probability translated into reason. And then there is the quantum arrow, subtler, more elusive. The wave function evolves symmetrically, but measurement does not. Collapse, whether real or only apparent, is irreversible. Decoherence disperses coherence into environment, scattering information, increasing entropy. At the smallest scales, the arrow is stitched into the act of observation. Each detection, each record, each choice is one way. Whether the universe branches into many worlds or collapses into one, the result is the same. No reversal, no recombination. The quantum arrow underwrites the thermodynamic one, for every macroscopic entropy increase is built from countless microscopic collapses and dispersals. The arrows nest like dolls, one inside another. When viewed together, the arrows are not parallel lines that happen to point the same way. They are strands in a braid, inseparable. The cosmological arrow sets the initial condition, the low entropy of the beginning and the expansion of space. The thermodynamic arrow grows from that condition, entropy rising in matter and energy. The quantum arrow gives irreversibility at the level of measurement, ensuring that information disperses and outcomes cannot rewind. The causal arrow emerges from entropy's gradient, turning probabilities into stories of before and after. And the psychological arrow crowns the structure, embedding memory and identity in the same slope. Each arrow leans on the others, each gives the others weight. Together, they compose the single experience we call time. Yet their unity is not without tension. The block universe of relativity erases the flow, while entropy restores it. Quantum mechanics offers reversibility in equations, while measurement insists on irreversibility in practice. Black holes seem to destroy information, while quantum theory insists it is preserved. These tensions show that the arrows are not perfectly aligned, but braided under strain. The braid holds, but its fibers pull against one another. It is in these strains that new physics may be found. Perhaps the arrows will one day be explained as one arrow, with entropy as its essence. Or perhaps entropy itself will be revealed as emergent, and the true arrow lies deeper, hidden in the foundations of space-time or quantum information. For now, what we can say is this: every arrow we encounter points the same way. The T cools, the stars expand, the wave function collapses, the cause precedes the effect, the memory looks backward. No arrow ever contradicts. There is no phenomenon that reliably runs time in reverse. The unity is empirical, undeniable. The future is always disorderly compared to the past. The past is always remembered, the future only imagined. The symmetry of laws never breaks this consensus. The arrows agree, and their agreement defines our world. The poetry of it is that time is not a single line, but a chorus of arrows. Each sings its own melody: entropy, expansion, memory, causality, measurement. But all harmonize into one song: forward. We live inside that song. It structures our physics, our biology, our stories, ourselves. It is why we grow old, why we grieve, why we hope. Without the arrows, there would be no narrative, no identity, no cosmos as we know it. The many arrows are one arrow, expressed in many dialects, and the arrow is time itself. As evening falls and shadows lengthen, the alignment of arrows feels almost comforting. Despite the universe's complexity, despite the mysteries still unresolved, the arrows point together. They tell us that there is order in the asymmetry, that the one-way street is not a glitch but a pattern. And though the destination of the arrow may be heat death, though the braid may end in silence, the journey it permits is everything. To live is to ride the braid, to feel its pull in every heartbeat, every memory, every star. The arrows weave the story of the universe, and we are pages in their book, written forward, never back. At night, when the body grows heavy and the mind drifts, the arrow of time seems to soften. Sleep does not erase the direction, but it reshapes our perception of it. Minutes can feel like hours, hours like moments. In dreams, events may run in strange orders, an ending before a beginning, a face from childhood suddenly joined with a place never visited. The ordinary sequence of cause and effect, memory and anticipation, bends. And yet, when we wake, the arrow reasserts itself with relentless clarity. The dream dissolves into fragments, and the morning light confirms that time has only moved forward. The theater of the mind becomes another mirror in which to study the arrow. Sleep itself follows a cycle, drifting through stages of non-REM and into REM, the phase where vivid dreams appear. Each cycle lasts about 90 minutes, repeating through the night. The pattern is not random. It is an arrow drawn by circadian rhythm, the biological clock wired into our cells. Hormones rise and fall, body temperature drifts, neurons fire in waves. The sequence is directional, never reversible. One does not leap from REM to waking and then return to the exact same REM as if nothing changed. The brain's rhythms, like entropy itself, march one way. Inside REM, the experience of time becomes slippery. A dream that feels like it lasted an entire day may have passed in minutes. The arrow is distorted, stretched, or compressed. Yet the distortion is not freedom from time, but another form of its rule. Dreams are stitched from memory, and memory, as we know, only looks backward. Even in dreams, the brain borrows fragments of the past, recombining them into new mosaics. A future may appear, but it is always the future imagined, never the future remembered. The arrow is never truly reversed. Even the most surreal dream obeys its deeper law. It draws from the past, never from what has not yet happened. Some dreams unsettle because they feel prophetic. A moment dreamed appears again in waking life, creating the eerie impression that the future was glimpsed. But careful study reveals the trick. The brain is a restless weaver, constantly recombining fragments into patterns. Now and then, coincidence aligns those patterns with reality, and the dream feels like foresight. But the record shows otherwise. The dream was built from the past, and the future matched by chance. The arrow holds. Prophecy is memory in disguise, a reshuffling that masquerades as foresight. Time in dreams also reveals itself in emotion. A nightmare accelerates, events rushing forward with merciless speed. A peaceful dream lingers, the minutes stretched into serene eternity. In both cases, the arrow is experienced through the body. The pounding heart, the rush of adrenaline, the calm of slowed breath. The physiology of sleep is directional. Neurotransmitters rise and fall. Brainwaves oscillate through predictable sequences. The arrow whispers through biology, even when the dream world ignores clocks. The dream bends perception, but it does not bend the current that carries us from one cycle to the next, from one night to the next, dawn. There is also the strange phenomenon of lucid dreaming, when the dreamer becomes aware that they are dreaming. In these moments, control seems possible. One can fly, change scenery, summon people long gone. Cause and effect appear pliable. Yet even here, the arrow asserts its quiet dominion. The dream ends, the body stirs, morning arrives. However liberated one feels within the dream, waking confirms that the flow of time has not been suspended. The lucidity was a temporary trick inside the mind's theater, but the stage itself never stopped drifting forward. Sleep also plays a role in memory consolidation. Experiments show that memories of the day are replayed during the night, neurons firing in patterns that echo the waking experience. The hippocampus rehearses, strengthening connections, moving traces into long-term storage. This process is irreversible. Once consolidated, a memory cannot be unencoded in the same exact way. Sleep writes the past into permanence, carrying fragments from fragile short-term circuits into durable networks. In this, the arrow of time is visible at the cellular level. Sleep is not escape from time, but one of its laboratories, a workshop where the mind shapes yesterday into narrative, preparing for tomorrow by sculpting what was. The metaphor of the theater of the mind captures the strangeness. In dreams, the stage is lit with scenes that do not obey ordinary causality, but backstage, the machinery is obedient to biology, entropy, and time. The arrows converge here, the psychological arrow as memories are replayed and rewritten, the thermodynamic arrow as the brain consumes energy and disperses heat, the quantum arrow as neurons fire through cascades of irreversible events. Even the cosmological arrow is present, for the very atoms in the brain were forged in stars that burned and died billions of years ago. The dream is personal, but the arrows that shape it are cosmic. To dream is to enact the entire universe's asymmetry in miniature. And when the dream fades, another arrow reveals itself, the forgetting. Dreams vanish quickly upon waking, details slipping like water through fingers. This too is entropy. The fragile traces decay, overwritten by the flood of sensory input in the morning. The past becomes irretrievable not because it never existed, but because information is scattered, lost in noise. Memory, whether waking or dreaming, is bounded by the same rule. Once entropy has erased the trace, the arrow has carried it beyond recovery. We might wonder what it would mean to dream backward, to close one's eyes and experience time running in reverse, ashes becoming paper, the dead rising into breath, words returning to mouths. Perhaps such dreams have been imagined in myth or art, but in biology, they do not exist. The architecture of the brain does not permit reversal. To dream backward would require entropy to fall, information to unscramble, neurons to unfire. The arrow forbids it, and so even in the surreal, even in the unbound freedom of sleep, time keeps its one-way direction. The dream bends perception, but cannot undo reality. In this sense, the arrow of time has an inner life as much as an outer one. The universe expands, entropy rises, causes precede effects, but the mind adds another layer, the experience of distortion, of elasticity, of dreaming. In sleep, we rehearse time's arrow in miniature, bending it but never breaking it. We learn that even the most fluid illusions cannot escape the current. The theater of the mind may dazzle us with nonlinear stories, but when the curtain falls, morning arrives, the arrow is waiting, unchanged, and so we sleep, we dream, we awaken. Night after night, the cycle repeats, carried by circadian rhythms, tethered to the turning of Earth, aligned with the cosmos. Our dreams are personal, fleeting, ephemeral, yet they are also another testament to the universality of the arrow. In them, we glimpse the strange possibility of time loosened, but in waking, we are reminded of time's rule. The arrow pierces both cosmos and mind, galaxy and neuron, dream and waking. And perhaps that is why dreams matter. They remind us that even when perception bends, reality flows forward, never back. Human imagination is restless. Even as physics insists that time runs forward, we dream of going back. Myths are filled with it, heroes slipping into underworlds where the past lingers, prophets who glimpse the future as if it were already written, stories where clocks can be rewound. Science fiction is haunted by the same longing. Machines that spin through years like trains through stations, portals that deliver us to other centuries. But behind the romance lies a paradox. If the arrow of time is irreversible, then time travel backward is more than difficult. It may be incoherent. To step against the arrow is to step into contradiction. The most famous of these contradictions is the grandfather paradox. Suppose a traveler journeys to the past and prevents their own grandfather from meeting their grandmother. The consequence is immediate. The traveler would never be born. But if they were never born, who traveled back to make the change? The chain of cause and effect twists into a loop that devours itself. The paradox is not merely logical. It reveals how deeply causality is bound to the arrow of time. To undo the past is not just forbidden by physics. It is forbidden by narrative. Stories collapse when causes and effects lose their order. Physicists have tried to imagine ways around the paradox. One proposal is the idea of consistency constraints. If time travel is possible, then events must conspire to prevent paradox. A traveler may go back, but every action they take will end up being part of the past all along. They cannot kill their grandfather because circumstances will prevent it. An accident, a hesitation, a coincidence. This is the Novikov self-consistency principle. It saves logic at the price of freedom, turning time travel into a stage where every script is fixed. But in preserving consistency, it also empties the fantasy of meaning. If the past cannot be changed, then traveling back is only tourism, not liberation. The arrow still holds, bending every possibility into alignment. Another idea is branching timelines. In this vision, going back and altering the past does not rewrite the history you came from, but creates a new branch, a parallel universe. Kill your grandfather there, and that branch evolves without you. But your own branch remains intact. The paradox dissolves, but only by multiplying worlds. The many worlds interpretation of quantum mechanics provides some inspiration for this model, suggesting that every quantum event already splits reality into branches. Yet the price is staggering, an infinite proliferation of universes, each carrying its own arrow of time. Even here, reversal is an illusion. You never truly change your past. You only create a different future elsewhere. General relativity, Einstein's theory, admits solutions known as closed time-like curves. In these spacetimes, paths loop back on themselves, allowing an object to return to its own past. Wormholes, if they exist and could be stabilized, might provide such loops. Science fiction seizes on these possibilities, imagining portals where one can step through to an earlier day. But physicists suspect that the universe conspires against them. Quantum effects may destabilize such curves, flooding them with energy and destroying the loop before it forms. If this cosmic censorship holds, then time protects itself. The arrow is not only stubborn, it is self-defending. And yet, even in mathematics, closed time-like curves are unsettling. If an event lies both in the past and future of itself, then causality is shredded. How does one distinguish cause from effect when both feed each other in a loop? Entropy becomes confused, memory unreliable, identity incoherent. To live in such a universe would be to live without the foundation of meaning. Perhaps this is why we recoil at the idea, why time travel paradoxes fascinate but disturb. They are windows into a world where the arrow bends back on itself, and in bending, breaks. The desire to travel backward is understandable. We long to correct mistakes, to save those we have lost, to relive joys, to undo griefs. Memory torments us with its asymmetry. We can look back, but not return. Imagination tempts us with reversal, but physics resists. The arrow is more than a line. It is the architecture of reality. To violate it is to dismantle the structure in which we live. Without it, the world is not just different, but incoherent. The paradoxes are not obstacles to be solved. They are warnings that the concept itself may be impossible. Even forward travel, which relativity allows through time dilation, highlights the asymmetry. An astronaut who moves near light speed may return to Earth to find centuries have passed. They have leapt into the future, but never into the past. The arrow permits leaps ahead, but never steps back. The one-way rule remains unbroken. The future is open, the past closed. No machine, no wormhole, no branch can erase that distinction. Still, Paradoxes serve a purpose. They sharpen our understanding of why the arrow matters. The grandfather paradox shows that causality and identity depend on irreversibility. Closed time-like curves reveal how entropy is tied to consistency. Wormholes test the limits of general relativity, forcing us to ask whether the universe itself enforces chronology protection. By wrestling with fantasies of reversal, we glimpse the necessity of the arrow. It is not a prison, but a framework. It is what allows stories to unfold, lives to be lived, histories to be written. Without it, even imagination falters. Late at night, one may dream of stepping through a door into yesterday, of seeing again a lost moment. But the dream dissolves upon waking. The arrow stands. The past remains untouchable, the future still unwritten. We are creatures carried forward, never back. The paradoxes are reminders that the longing is natural, but the reversal impossible. Time's arrow pierces every possibility, bending imagination, but never breaking itself. And perhaps that is merciful. For a world without the arrow would not be a world at all, but a loop without meaning, a story without coherence. The impossibility of reversal is what gives weight to every moment, what makes each instant precious, what turns history into story rather than static geometry. The arrow forbids us from going back, and in forbidding, it gives us life. The journey has carried us across many landscapes. The entropy of broken cups and shuffled cards, the expansion of galaxies, the collapse of quantum possibilities, the loops of causality, the fragile theater of memory and dream. Each domain seemed to tell its own story, but all their arrows pointed the same way. Now, in gathering them together, we begin to see that perhaps they are not separate arrows at all, but facets of one deeper current. The climax of the riddle is the realization that time's direction is not a patchwork but a chorus, all voices singing one melody. Forward. Entropy is the anchor. From the second law of thermodynamics, we know that systems move from improbable order to probable disorder. This is not a force, but a statistical destiny. Milk will not climb back into the glass because there are far more ways to be spilled than to be whole. Entropy is probability translated into experience. And yet, entropy alone is not sufficient. Its story needs a beginning. The low entropy of the Big Bang provides that starting point, a baseline improbably smooth and ordered, from which all later disorder could grow. Without that strange beginning, entropy would have no slope to climb, no arrow to draw. The cosmological arrow provides the canvas. The thermodynamic arrow paints upon it. Memory and causality are born from this canvas. We remember the past because it left low entropy records, footprints in sand, neurons firing, ink on paper. We never remember the future because it has not yet created records. Memory is entropy's shadow in the mind. Causality, too, emerges from this asymmetry. Causes precede effects because entropy flows in one direction. The shattering of a vase is more probable than its reassembly, and so we experience the former as cause and the latter as effect. Our logic, our stories, our identities, all lean on this slope. The psychological and causal arrows are not independent. They are human translations of entropy's climb. Quantum mechanics deepens the weave. The wave function evolves symmetrically, but when measured, possibilities collapse into facts. Whether collapse is real or only an appearance through decoherence, the outcome is irreversible. Information is dispersed into the environment, entanglement spreads, entropy rises. Quantum irreversibility gives microscopic teeth to macroscopic entropy. Every recorded outcome is an act of entropy growth. Every click of a detector, another step in the arrow. Even the smallest scales refuse reversal. The quantum arrow is the seed. The thermodynamic arrow is the forest that grows from it. And overarching all is the cosmological arrow, the expansion of the universe. Galaxies rush apart, space itself stretches, the temperature of the cosmos falls. The expansion sets the direction of history, smaller and hotter behind us, larger and colder ahead. It is in this gradient that entropy finds room to grow, that stars ignite and die, that complexity arises as temporary islands of order in an expanding sea. The cosmological arrow gives the thermodynamic arrow its slope, and together they carry the quantum, causal, and psychological arrows with them. The universe is not a stage for many arrows. It is one unfolding in which all arrows are braided. Seen this way, the paradoxes resolve into coherence. Loschmidt's challenge, Why reversible laws produce irreversible outcomes finds its answer in the improbable low entropy of the beginning. The psychological arrow, why we remember the past but not the future, becomes clear when we see that only the past has left low entropy traces. The causal arrow, why causes precede effects, follows because entropy selects one direction for probability to flow. The quantum arrow, why measurement is irreversible, reflects the dispersal of information into entanglement, aligning with entropy. The cosmological arrow, why the universe expands, anchors all, providing the initial asymmetry that made the others inevitable. The many arrows are one, refracted through different prisms. And yet, this unity is not trivial. It raises as many questions as it answers. Why was the entropy of the early universe so low? Why does space expand at all? And why is that expansion accelerating under the influence of dark energy? Why does decoherence create irreversibility instead of allowing recoherence? The arrows converge, but their convergence points to mysteries still unresolved. To understand time's arrow is to stand at the edge of knowledge, where the known threads into the unknown. Coherence does not mean closure. The climax is not the end of the story, but the recognition that the story itself has a shape. In that shape lies meaning. The arrow of time is not merely a physical fact. It is the condition for life, for memory, for identity. Without it, there would be no growth, no decay, no evolution, no history. A universe without an arrow would be a static block, timeless, lifeless, without story. We live because the arrow exists. We tell stories because the arrow flows. Every joy and every grief, every rise and every fall, every memory and every hope is a gift of entropy's asymmetry. The price of irreversibility is loss, but the gift is meaning. To go forward is to live. To go backward is impossible. That impossibility is what makes each moment precious. Imagine again the broken clock on the wall, its hands frozen, its face cracked. In the stillness of the object, entropy is still at work, dust settling, air molecules bouncing, the wood warping. Even when time seems still, the arrow is present. The universe does not stop. It only hides its movement. The clock is not only a metaphor for decay, but for coherence. It reminds us that time is not one thread, but many, all pointing the same way. Even broken, it belongs to the flow. Even silent, it ticks in entropy's language. The coherent picture, then, is not that the arrows are illusions, but that they are perspectives on one truth. Entropy rises. From that rise comes memory, causality, quantum irreversibility, cosmic expansion. The arrows are not separate arrows, but facets of entropy's climb. The arrow of time is not one phenomenon among others. It is the foundation upon which all phenomena rest. To live in time is to live in entropy, to ride its slope, to be written in its script. At the climax of the riddle, we see not a single equation, but a unity of experience and physics. Time's arrow is the convergence of probability, expansion, measurement, causality, and memory. It is the bridge between the symmetry of laws and the asymmetry of life. It is the reason the universe has history, and the reason we have selves. It is both the simplest fact that milk spills and the deepest mystery that the universe began ordered. The coherence is fragile, beautiful, unfinished, but it is enough to tell us why we move forward, never back. The room is quiet again. On the wall, the broken clock still hangs, its glass fractured, its hands unmoving. At first glance, it looks like the very image of timelessness, as though the arrow has been arrested. But, of course, the stillness is an illusion. Dust gathers on the rim. Light fades through the window, shifting its shadows across the floor. The wood of the frame warps imperceptibly. Molecules drift, air currents change, and with each change, entropy increases. The clock does not tick, yet time ticks through it. The arrow has not stopped. It has simply chosen subtler instruments. We have followed the arrow through many realms. In the shattering of glasses and the cooling of tea, in the expansion of the universe and the collapse of stars, in the irreversible clicks of detectors and the fragile continuity of memory. In each, the arrow points forward, never back. We have seen its paradoxes, why the laws are reversible yet the world is not, why the universe began improbably ordered, why black holes seem to consume information, why time travel entangles itself in contradiction. We have seen its unity, entropy as the thread that weaves quantum, cosmological, psychological, and causal arrows into one braid. And now we stand at the end of the journey, knowing that the arrow is both obvious and mysterious, both familiar and unfathomable. It is obvious because we live within it every second. We age, we remember, we anticipate. We cannot undo what is done. The arrow is woven into our lives so deeply that to doubt it feels absurd. And yet it is mysterious, because at the heart of physics, the laws are symmetric. Nothing in Newton's equations, in Schrödinger's wave function, in Einstein's space-time, prefers past to future. The asymmetry emerges only in the improbable initial condition of the cosmos and in the statistical avalanche of entropy. The arrow is both everywhere and nowhere, both the most basic fact of existence and the most puzzling. It is the paradox that makes reality habitable. What then are we to do with this knowledge? If the universe is doomed to heat death, if entropy must always rise, if time is irreversible, should we despair? Perhaps not. For the arrow that carries us toward disorder is also the arrow that made stars ignite, that made planets coalesce, that made life possible. It is because entropy rises that energy flows, and because energy flows that complexity emerges. The arrow that guarantees our eventual end is also the arrow that gave us our beginning. It is the condition of loss, but also the condition of possibility. To lament the arrow is to lament life itself. We are, in a sense, temporary eddies in the current of entropy, small pockets of order sustained for a while. Our bodies, our minds, our cultures, all are local reversals bought at the cost of greater disorder elsewhere. We live because we burn fuel, consume energy, release heat. We think because neurons fire, scattering entropy outward. We tell stories because our memories inscribe traces while the future remains blank. The arrow is not just outside us, it is inside us. It is the architecture of being. To live against it would be to live against the condition of existence itself. And yet, within that current, there is room for freedom. The future may be constrained. It will be higher entropy than the past. But it is not predetermined in detail. Within the slope, countless paths are possible. The arrow tells us only that disorder grows. It does not tell us which stories will unfold along the way. We cannot return to yesterday, but we can shape tomorrow. The arrow forbids reversal, but permits creation. It closes one door, but opens another. The door of becoming. The future is not remembered, but it can be imagined, chosen, made. The arrow carries us forward, but how we walk within it remains our story. The broken clock on the wall is a reminder. Its hands are frozen, but our lives are not. We move through moments that cannot be reclaimed. Each breath is irreversible, each heartbeat unique, each word spoken a step further along the path. The fragility of time is also its beauty. If everything could be undone, nothing would matter. It is the irreversibility that gives weight to memory, to love, to grief, to joy. We cannot rewind, and so we cherish. The arrow, in forbidding return, grants significance to the journey. Look outward now, beyond the room, into the sky. The galaxies recede, the stars age, the universe cools. The expansion writes a future of silence, yet the present is filled with light. We live in a moment when the sky is still bright, when the past can still be read in starlight, when the arrow still carries stories not yet told. To be alive now is to inhabit a narrow window in cosmic history, a time when entropy has risen enough to create complexity, but not yet enough to erase it. We are children of the arrow at its most fertile, its most creative. The future may belong to silence, but the present belongs to possibility. And so we close with humility. The arrow of time is larger than us, larger than our planet, larger than our species. It is the river that began at the Big Bang and will not end until the last whisper of heat is spread thin across infinite space. We are but eddies in that current, brief and fragile. But in our brevity, we have the chance to know, to see the arrow, to ask why it exists, to trace its path from entropy to memory to stars. The cosmos has given us not only existence, but awareness of existence, not only time, but reflection on time. That awareness is itself a miracle of the arrow, an emergent spark within its flow. The broken clock does not tick, but the universe does. Its ticking is not sound, but change, not rhythm, but entropy. Each moment passes irretrievably, and each is irreplaceable. The arrow does not let us return, but it lets us live. And as long as we live, we can tell its story. We can look backward with memory, forward with imagination, and inward with wonder. The arrow is not our enemy. It is the path itself. And when it finally carries us beyond memory, beyond story, beyond life, it will still carry the universe forward, silently, endlessly.